Thanks for tuning into this episode of QRP to QRO. This is video number 5.1, Elecraft K2 Bandpass filter shapes explained. So in my previous video, number 5, talking about a method of using a tracking generator and spectrum analyzer for tuning the bandpass filters, one of the questions that came up was, why does the filter shape for 160 meters look the way that it does? So we'll talk about that in this video, and I'm also going to go through all the different band filters so you get a better idea of what the shapes are for those filters as well. So to start off with, let's take a close look at the schematic. And again, the band that I'm going to focus on here is 160 meters, but as you see, it is in combination with the 80 meter band as well, and which components are used is what determines which band, and the switching is done by these relays. There's actually two of them. This one down here is K3, and then you have two poles of relay K2. So you got side A and side B. The general idea to wrap your mind around here is that if you put inductors and capacitors together, they will have some frequency of resonance. So you see that here on the left side, you can also see that over here on the right side. One other major point to consider as well is that not only do these components matter, but their placement and the circuits themselves have an effect as well. So you have inductance along traces, and you also have capacitance between traces that adds into the overall resonance of this particular portion of the circuit. So there are multiple factors. I won't go into all of them in very much detail, but I just want you to have that picture in your mind as we go through this. So moving along here, another idea that I want to bring up is that of quality factor, or the Q factor. And what that equates to is reactance over resistance. Or another way to think about it is the stored energy over dissipated energy. And what that comes down to is the higher this value, the more efficient the power transfer is through that circuit. And also, the higher that you go with the Q factor, the more narrow band that frequency response ends up being. And the reverse is also true. The lower this Q factor, the less efficient that circuit is, and the more broadband that frequency response is. So if we graph that a little bit, and this isn't going to be perfect, it's just going to be a quick visualization. Again, if we put an inductor and a capacitor together at some point of resonance, those values will be most efficient. So we'll represent that here in the center with the resonant frequency. And then negative is lower in frequency. Positive is, again, higher in frequency. And then in the middle, again at the resonant frequency, I'm not putting any numbers to this, it's just a visualization. You have some ideal point of resonance. And as you go down in frequency, you're going to have some signal attenuation. As you go higher in frequency, you'll also get attenuation. And going back to that Q factor, the higher this is, the more narrow and narrow that frequency response gets, and the opposite too. The worse that quality factor is, or the lower the value is, the more broad that this frequency response is going to get, both above and below the resonant frequency. And again, I'm not going to put numbers to this right now, it's just a pictorial. So if we expand this out a little bit, let's go to the 160 meter circuit. So looking at the components again, you have inductors and capacitors on the left side, and you have the inductors and capacitors on the right side. So you really have two halves of the circuit to play with. So looking back at the graph, we'll describe that here with 2 resonant frequencies. And again, I'm not going to put numbers to this, just a pictorial. So you have some resonance here, and then on the right half, you're going to have some resonance over here. And again, with all the multiple factors of even the components within the circuitry itself, the traces having inductance and capacitance as well, there's a ton of different factors that go into what creates the overall shape of these filters. But the general idea is that you're going to have some ideal resonance within each section of each circuit, each bandpass filter circuit. And on the 160 meter band, being as low a frequency it is, you're going to have the most pronounced frequency response of each half. So let's take a look at that inside the radio now. So another quick point to make also on the 160 meter band and 80 is there's an additional inductor here in the middle. So what I'm going to do to pictorialize each half and the frequency response is I'm actually going to tap each side of this inductor depending on which half that we're looking at on the spectrum analyzer in just a minute. So let's go ahead and open up the radio. I'm not going to disconnect the speaker this time because I'll point something else out as well as we go through this. So I didn't have enough light a minute ago, so I just turned another light on, give us a better look inside the radio here. So as I mentioned before on the schematic, there's our additional inductor L5. So what I'm going to do is I'm going to tap between D7 and L5 and also between W6 and L5. And that way we'll get each half of the 160 meter filtering independently of each other. So we can see that on the spectrum analyzer. So what you're looking at here is the frequency response of the 160 meter bandpass filter. And this is the whole thing combined. So let's take a look at each half of it independently. And again, this is an installed circuit, so all of these components do interact with the traces. So you have, again, inductance along the traces and capacitance between them. And you also have interaction with the other components that are adjacent on the board. So we're not getting a perfect frequency response on each half, and that's why you see this somewhat flat top. But the point I'm trying to get across is each half of that filter is almost its own section. So we'll look at the other side just to pictorialize that as well. So now we're on the opposite half, and then if we put both halves together through the whole filter now, we have that same, I'll call it funky looking frequency response. And then to illustrate it a little bit farther, what I'm going to do is tune L3. Now we'll go back the other way with it here just to broaden that response. So now I've moved L3 just a little bit. I'm going to do the same thing this time with L4. And we're going to widen that frequency response. So now we're moving the right peak. And again, the point I'm trying to get across is each one of those peaks is resonant at a particular frequency. It just so happens that at this frequency, with all other factors, including the quality factor that I mentioned here a minute ago, we get that dip in the middle. It's, again, just so on this particular frequency or band that those two peaks are as pronounced as they are. So we'll go ahead and bring this back to about where we had it. And again, in my case, I'm trying to peak that lower peak to 1815. That's where I want it for my radio. You can pick whichever frequency you want to tune yours to. So there, we're about where we had it. So now while we're at it, let me go to the 80 meter band, and we'll do an illustration of the bands here. So that frequency changed, and I've got the filter set on the radio. We'll see our signal coming up. I'm going to make two changes in the screen also. I'm going to decrease the reference level, make it a little bit more sensitive. I'm also going to change the width to 2.5 megahertz, because then we can see a more broad picture of that response. That'll come in handy with some of the other bands as well as we go along. Then we'll bring the marker up and highlight both the band edges. So there's our bottom around 3500, and then I'll change the delta marker and put that up to about 4 megahertz, which would be 500 kilohertz higher. So again, in my video 5, I think we're hovering around -9 dB difference between the bottom and upper part of the band. We're about -10. Yeah, let's see if we can dial that in just a little bit here. Not that it makes a whole lot of difference, but just for the sake of discussion. So we'll see that starting to come up a little bit now. So there we go, we're setting about 9 dB difference. Again, between the lower part of the band down here and then the upper part of the band. So we'll move on to 40, take a look at that band here. Again, we'll try to pick the middle of the band. And there's the top of the band at 7 megahertz. Put our delta on. There's about the top of the band. So you can see we're getting pretty much the band within the peak of that frequency response of the 40 meter filter. We'll move on to 30. Oops. 10 point, what is that? 125 is the center of that band. We'll go back to the marker. And the main will set at 10. And our delta we'll put at 1050. Oops, I'm sorry. No, the bottom of the band is 10.1. I'm sorry. Okay, there's 10.1. Bring up our delta. Change that to plus 50. So narrowest band there's not a whole lot of difference, but just for the sake of discussion and visualization, there it is. So we'll go to 20. Let's see, 14.350, that's going to be 175 is the midpoint there. We'll go back to the marker. And we'll put the main at the bottom at 14. And we'll go to the delta and put that at the top at 350. Or thereabouts. So again, just for sake of discussion and visualization, You can see in between the markers is where the 20 meter band is. And we'll go to 17 meters. So 18068 to 18168, that would be 108 in the middle. So again, it's a narrow band like 30 is, but that gives us a rough idea of where that band lies within the filter response. We'll go to 15 meters. Let's see, that's 450 on the top end, so 21.225 should be the middle of that band. We'll change that marker. The main being right at 21. And the delta will go up to 450 or thereabouts. So you can see where the band lies within the visualization here on the screen. We'll go to 12 meters. So that's what, 24,890 to 24,990. So that's going to be, what is that, 910 in the middle? So there's our main right about 24,890. Bring up our delta and 1 megahertz up or close to it. Again, a narrow band, so it falls right in the middle of the frequency response of the filter. And then another funky band is 10 meters. So 28 to 30. So we've got 29 right in the middle. So we're up 2 megahertz between the main marker and the delta in this example. Let me get my coordinate here. But we're also only focused really on the bottom half of the band, because once you get up in this region, it's FM. So really the band portion that we're going to focus on with 10 meters is only up to about 28.5, and even, you know, like I set the center at 29. So we'll put this delta 1 megahertz up. So again, we've got 28 on the bottom and then 29 in the middle. Even still, if we go up this high, we're still not going to be on this radio because it doesn't do FM anyway. We're not going to be focusing on that portion of the band. So really, if you go to the sideband portion, topping out at about 28.5, then you're really right smack in the high point of where this filter response is anyway. If I zoom out a little bit just for the sake of discussion also, let's bring this up to a 4 megahertz span. So you can see that when you do get out of the band on the bottom side, let me turn my delta marker off. And then 28 megahertz is right there. So you can see pretty soon after the bottom of the band, we really do start rolling off in that frequency response. So again, if we're concerned with out-of-band emissions and sensitivity, then this filter does chop off quite a bit. So I'm going to go back to 160 meters for a minute and just point out the tracking generator functionality. I'll go ahead and turn the volume up on the radio and you can hear exactly what it sounds like. So if you hear that ticking in the background, that's the signal that's coming out of the service monitor. And what it's doing is it's actually sweeping a wide range of frequencies all the way through the span that we have set up on the screen. So if we go back to our span, you can hear that ticking change. So what it's doing is sending out a signal and measuring the response simultaneously throughout the range of frequencies that are being displayed. So just for example, if we take this off of tracking, I'm going to turn the volume down so we don't get blasted here. I'm going to put this to a discrete or fixed frequency. So now we have just a constant tone. And again, all the tracking generator is doing is it's sweeping a response so that we're able to measure not just one point, but the swept frequency response, in this case of a filter or any other component that has a frequency range to it. That about wraps up this edition of QRP to QRO, video 5.1. Filter shapes explained in the Elecraft K2. I hope this was able to answer the question and put a little bit better visualization to the filter shapes and what goes into them. Again, it really comes down to the interaction between inductors and capacitors, but there are other factors to keep in mind as well, such as the reactance with the traces themselves and the interaction with other components in the same circuitry. My name is Steve, and my amateur radio call sign is KC8QVO. If you like what you've seen in my videos and find them helpful in your own amateur radio endeavors, please click on the subscribe button under the bottom right of the screen. You can also follow me on Twitter at QRP2QRO. Feel free to ask any more questions. Thanks for watching.